Hello, and welcome to our very first rational functions video. This is the 3.4, I'm going to erase that too, the 3.4 video where we're going to just be talking a lot of things about rational functions. I'm going to be throwing a lot at you, so let's get started. This first box right here tells us what a rational function is, and it's essentially one polynomial over another polynomial. Now, the zeros of a rational function occur when p of x is equal to 0, as the function's value is 0 when the value of the numerator is 0. That was the word 0 several thousand times, so I'm going to rewrite that in words that we may be able to understand. So the zeros of the numerator, so we're talking the top of the fraction right now, so in this case that's p of x, are the x values of the horizontal intercepts. So basically what that means is that if you want to find your horizontal intercept, you got to look at the numerator. Now I'm going to caveat this with most of the time. The only time when that's not true would be when holes are involved, and you're going to learn about that at the very end of the video. And then the next line is, a rational function is undefined when q of x is equal to 0, as the function is undefined whenever its denominator is 0. So this goes back to our domain restrictions of, hey, you're not allowed to divide by 0. So what it's really saying here, I'm going to move this over, is that the zeros of the denominator so in this case, q of x indicate the presence of a discontinuity. I'm going to underline that because that's important. In the domain. So this discontinuity might be a few different things. Normally, it's just going to be a vertical asymptote. So look to your denominator if you want to find a vertical asymptote. But this might also be a hole. So like I just said, we'll learn more about that at the end of the video. But if you have a hole, that's going to affect both your numerator and denominator. So that's a little bit about those functions. Let's start building some parent functions, because we do in fact have more than one. So in this first graph right here, we have y is equal to 1 over x. I'm going to fill out this table for us fairly quickly. But basically, if we go through and we plug in all of these values into 1 over x, anytime we plug in a whole number, we're going to get a fraction. Every time we plug in a fraction, we're going to get a whole number. So if I plug in -4, I'm going to get -1/4. -1/2, -1. Now if I do 1 over -1/2, that's going to get me -2, -4, and then if I plug in 0, anything divided by 0 is bad. So we're just going to say that's undefined. And then we'll do our positive side. So this will be +4, 2, 1, 1/2, and 1/4. Sorry, I know I went through that kind of fast. So we have something that is undefined. So since that's undefined, I'm going to call that an asymptote and say that's a boundary we can't cross. So that's going to be when x is equal to 0. So that's going to be along my y-axis right here. This is my vertical asymptote. So now that we've got that in, let's plot all of our points. Thank you for your patience while I do this. So let's see, at 4 we have 1/4, 2 we have 1/2, 1 and 1, and then we have 2 and 1/4. And again, do graph 1/4 and 1/2 the best that you can. These are not going to be super exact. There we go. So when I graph all of my points, I'm going to have two separate pieces here, and you'll notice they never quite, I have muted myself, I'm sorry, they never quite reach that x-axis. They kind of run along it but never quite reach it. That's going to be another asymptote of ours. That is going to be our horizontal asymptote, another boundary or barrier. So we're going to put that right there. So this is what our parent graph looks like for 1 over x. The next question asks, list any horizontal and vertical asymptotes and the long run behavior of the function. So for us, where would you guess? Okay, so for our horizontal asymptote, which I will be shortening to HA, since horizontal and asymptote are two very long words. Since it runs along our x-axis, that's always going to be y is equal to 0, since that's where our y value is always equal to 0. And then for our, oops, I misspelled vertical, that's my bad. Where's the eraser? For my vertical asymptote, which I will be shortening to VA, that runs along our y-axis, so that's when x is going to be equal to 0. Please don't just write 0, please write y is equal to or x is equal to for all the appropriate pieces. And then lastly, we have our long run behavior, which we've been dealing with in our last unit. And the cool thing about long run behavior is that your long run behavior, the RLB, is the same as your HA, or your horizontal asymptote. So wherever your horizontal asymptote is, that's where your arrows are going. So we can say that as x goes to negative infinity, f of x goes to 0, and as x goes to infinity, f of x goes to 0. So remember, 0, that's our horizontal asymptote. Here we're talking about a left arrow, oops, I started writing the word arrow, left arrow and right arrow, and those are both heading towards 0. So this is our parent graph for 1 over x, but what if we have something a little bit different? What about if there's a power in the denominator? So what about 1 over x squared? What is that going to look like? This is in fact a different parent graph depending on what we're dealing with. I'm hoping that you've seen the first one before. You may not have seen this one. So first we're going to create a table, plug everything into 1 over x squared. Again, if you plug in a whole number, you're going to get a fraction. If you plug in a fraction, you're going to get a whole number. But since we're squaring anything we plug in, all of our answers should be positive. So for instance, if we plug in a negative 4, we should get 1 over a positive 16, because negative times negative is a positive. We'll also get negative 1/4, positive 1, 4, and 16 here. And then no matter what, if you plug in 0, 0 squared is still 0. So that's going to be undefined. If I plug in a 1/4, that's going to give me 16, 4, 1, 1/4, and 1/16 again. So when I graph this, this is going to look, still have that weird curve to it, but be just a little extra special. Now we're not going to be able to graph all of this because 16 definitely goes off the graph, but that's okay. I think we'll still get a good idea of what we are looking for. So let's see, this goes about here. 2 is 1/4, 1/16. We'll say that's there. So this is what my positive side looks like with my positive x values. And then my negative x values, we're still doing some really positive stuff here. It looks something like this. So now instead of being in opposite quadrants like kitty corner to each other, whenever we have 1 over x squared, both the ends are facing the same direction, both are positive, because anything squared is going to be positive. Now let's draw in those asymptotes. So for us, we're going to have a vertical asymptote when x is equal to 0, because that gave us something that was undefined. And again, here I can see that we're getting really close to the x-axis, but don't quite reach it. So I can see here that my asymptotes are actually the same as 1 over x. So my horizontal asymptote is still going to be y is equal to 0. And my vertical asymptote is going to be x is equal to 0. And the cool thing is that for the long run behavior, the rules still apply. So whatever we have for our horizontal asymptote, that's where our y values are going to go. So as x goes to negative infinity, f of x goes to 0. And as x goes to positive infinity, f of x still goes to 0. So these are two of the rational functions that we are going to be dealing with. Now, what does it look like if we have different powers? So instead of 1 over x squared, what if it's to the 4th or to the 6th or 1 over x to the 5th? What would that look like? So if we scroll down here, there we are. This came out in color, which is kind of nice. We can see that things, I'm gonna change this. I'll just do an actual laser pointer. So we can see things get a little flatter along here the higher the power gets. So the dark blue here and here are going to be our highest power. So this got really flat, really flat, really flat, really flat, flat. We're going to be dealing with the red stuff. Except for over here, we're not going to be dealing much with 1 over x cubed. We're going to be dealing more with 1 over x, which they don't actually have graphed here. But this 1 over x squared, that's something we can deal with. So we're going to be using those parent tables and those parent graphs to help us graph some of our transformations. Throwing it back to Unit 2. So let's look at that transformational form. So there's a few different types of forms for rational functions. For transformational form, you're going to have a over x minus h plus k. And you might be like, those letters seem very familiar. Oh, I forgot the M in form. There we go. Those letters seem very familiar. And that's because they are familiar. The K is a vertical shift, moving us up and down. The H is a horizontal shift, moving us left or right. And the A value is a vertical stretch or compression. For right now, don't worry about the B values for our transformational form. So if I take a look at this problem right here, this first example, this is very similar to 1 over x, except we have this minus 1 here. So what that means for us, where is my pen? There we go. What that means for us is, oh, that's going to be a horizontal shift, or the whole graph is going to be moved to the right 1 unit. So we're just going to take our parent graph that we originally had, move it all to the right 1 unit. But first, I'm going to graph my asymptotes, find and graph my asymptotes. So for our horizontal asymptote, nothing has changed from the first one. We don't have any k value. We don't have any of that shift. So our horizontal asymptote is still going to be y is equal to 0. But for our vertical asymptote, now remember that comes from the denominator or the bottom of our fraction. So we're going to take that x minus 1, set that equal to 0, and solve. So we're going to have an asymptote at x is equal to 1. So that's going to be our vertical asymptote. So if I'm going to graph my asymptotes, my horizontal asymptote is going to stay the same. And my vertical asymptote is now going to be shifted 1 to the right. So what I'm going to do is I'm going to graph the points. I'm going to do some sliding here. I'm going to graph the points that we see right here for our parent graph of 1 over x, except I'm going to be adding 1 to all of the x values, therefore just shifting it 1 to the right. So I'm going to slide back. So feel free to take a moment, try it on your own with that previous table. I'm going to do that. Oops, we want the blue now. It's going to look something like this. So just get those points on there to the best of your ability. Okay, there's the first part, and then we have our second part here. And here is our graph. So when we find our long-run behavior, sorry, that took me so long to write. So for our long-run behavior, remember, a long-run behavior always goes towards whatever our horizontal asymptote is, in this case, 0. So as x goes to negative infinity, we're not dealing with r of x. R of x is going to go to 0. And as x goes to positive infinity, r of x is still going to go to 0 because they're going along that horizontal asymptote. The last thing, there's an extra thing. This question asks us to find the domain and range of this function. We can actually have all of these points, all the points for all of our x's and all of our y's, except for these boundaries that we cannot cross, called our asymptotes. So for our domain is going to be from negative infinity to 1, and from 1 to infinity, since that's the one x value that we're not allowed to have. And then for our range, the one y value we're not allowed to have is when y is equal to 0, or our horizontal asymptote. So our range is going to be from negative infinity to 0, and from 0 to infinity. So we're just transforming our parent graphs, moving them all around. Let's try that again, but with the second parent graph, with the 1 over x squared. So let's take a look over here. We have a few other things happening right now. So let's see. I don't have space to write all of the transformations, but if I take a look here, okay, this x minus 3, that's going to be moving to the right by 3. And that minus 2 at the very end, that's kind of like our plus k, that's going to be moving everything down. So if I want to go through and find my asymptotes, my horizontal asymptote is going to be from any shift up or down, and I see that we've been shifted down 2. So instead of having a horizontal asymptote at y is equal to 0, it's now going to be at y is equal to negative 2. And our vertical asymptote comes from the denominator, so we're going to take that x minus 3, set it equal to 0, solve for x, and we get x is equal to 3. So let's graph those asymptotes. So it's going to be at y is equal to negative 2. And notice that I do these with dashed lines and not with solid lines. Please do not use solid lines when graphing these. Okay, so we have our asymptotes. Now what I'm going to do is I'm going to slide again, and we're going to go back to this parent graph. So I'm going to take these points from either the graph or the table, your choice, and we're going to be subtracting 2 from the y values, or shifting them down 2, and we're going to be adding 3 to the x values, or shifting them to the right 3. So feel free to take a moment to do that on your own. So you'll notice that since it's been shifted so far to the right, you're not going to have a lot of that right piece. That's okay, just do what you can to the very best of your ability. It's going to be about there. So like I can really only fit about 2 points, but you know, I know it's supposed to curve this way. And then for my next one, this will go here. So also be about right here. I have one here-ish and here-ish. So again, just to the best of your abilities. It's on a graph like this, it's hard to differentiate between a point of 1/4 versus 1/6. Let's get to the rest of the features. So for the long run behavior, again, this goes to the horizontal asymptote, but it's no longer 0. So, oops, the line. As x goes to negative infinity, r of x goes to negative 2. So we're like past 0, it's fine, but we're getting real close to that negative 2. And then we'll have the same thing for our left arrow. So, pardon me, our right arrow. So as x goes to infinity, r of x goes to negative 2. Now for our domain, it's going to be very similar to the previous problem. We have a break with a vertical asymptote at x is equal to 3. So this will be from negative infinity to 3, and from 3 to infinity. But our range is going to look a little bit different, and that's because we don't have anything down here. We start at 2, and then we go up. And that's because we're dealing with a parent graph of 1 over x squared, where we have our graph in, if you want to think of them like quadrants 1 and 2. So our our range here is actually going to be parentheses 2, negative 2 to infinity. And that's it. You don't have the previous piece, you don't have another interval, because that's just all the possible y values you can have. All right, we have 2 more problems to get through, and then we're going to leave the last 2 for the Go formative. Let's get to it. So in this next question, we're going to be looking for zeros, or horizontal intercepts, and vertical asymptotes. And it says to factor each expression first and reduce to the lowest term if necessary. So make sure that you are factoring to the best of your abilities. I'm also going to include one more thing on here, because it's going to be in one of my examples, and it's going to be in your homework. Holes. We're going to be solving for holes. Like I said, we would be talking about that. So I'm going to do A and B, C and D are for you to do later on. So let's take a look at A. So A is r of x is equal to 3 over x squared minus 4. So I look at this x squared minus 4 and I go, okay, I can factor that. That's a difference of squares. This becomes 3 over x plus 2 times x minus 2. Nothing cancels out. That's okay. I'm just going to keep going with what we need to do. So let's see, for our horizontal intercepts, or our zeros, the way we find horizontal intercepts or zeros is we always set the whole equation equal to 0, because you have an x-intercept when your y value is 0. So we're going to say 0 is equal to 3 over x plus 2 times x minus 2. So I get to here. Now I'm going to multiply both sides by the denominator. So x plus 2 times x minus 2. Well, 0 times anything is just 0. So we get to 0 is equal to 3. But that's not how math works, right? 0 is just not the same as any other number. So these things are not actually equal to each other. So we can say there are no zeros. If we come up with something like this that just doesn't make any sense, maybe there are no horizontal intercepts, and that's okay. So I'm going to say, therefore, no horizontal intercepts. If you get x is equal to something, there's a horizontal intercept, but in this case, if you get down to something that doesn't make sense, that's okay. It just means there isn't any. So that's the first piece we want to find. The next one is our vertical asymptotes, where we set our denominator equal to 0. And in this case, since we've already factored, I can just set both factors equal to 0. So we'll say x plus 2 is equal to 0, and x minus 2 is equal to 0. So our actual vertical asymptotes are going to be x is equal to negative 2, and x is equal to positive 2. So in this case, we have 2 vertical asymptotes, and that's okay. Please notice that I did x is equal to. Don't just tell me negative 2 and 2. Please use the proper notation. That's it. Let's move on to part B. So this looks much more factorable. So let's see, I take a look at this. In my numerator, I can factor a 3 out of both these pieces. So this is going to be 3 times x minus 2. And if I look at my denominator, let's see, 2 numbers that multiply to negative 6 and add to 1 are going to be positive 3. So it'll be x plus 3. And it's negative 2. So x minus 2. So I take a look at this and I go, oh, x minus 2 on top, x minus 2 on bottom. I can cancel those out. And I'm going to be left with 3 over x plus 3. That looks a lot easier to deal with. I'm going to stick with that. So when we deal with our horizontal intercept and our vertical asymptote, we're going to be dealing with our new reduced equation. We'll deal with that x minus 2 in just a little bit. But first, let's get to our horizontal intercepts. Horizontal intercepts. You can also shorten this to HI if you'd like to do so. So I'm going to do the exact same thing as above. I'm going to set my whole equation equal to 0. I'm going to multiply both sides by the denominator, but 0 times anything is just 0. So again, I get 0 is equal to 3. Oh, but that's not true. That's not a real life actual thing. So we're going to say there are no horizontal intercepts. Okay. If you do find a horizontal intercept with x is equal to, please just write it as a point with your x value, comma, 0, since that is your y value. Next, let's look for our vertical asymptotes. Now remember, we're dealing with the reduced version here, so I'm not going to set x plus 3 equal to 0 and x minus 2 equal to 0. I'm just using the x plus 3. So when I solve for this, when I say that my actual vertical asymptote, we're only going to have one, is that x is equal to negative 3, and that's it. So those are finding the first two pieces. What about these holes that we've been talking about? Well, a hole, I'm going to change my color here. A hole are factors that reduce, leaving like an actual hole, like a physical open point in the function. So in our case, we had x minus 2 reduce away. So that's something that we found top of our fraction and bottom of our fraction. That reduced away. So we can say there is a hole at x is equal to positive 2. So I set that factor equal to 0, solve for it, here we are. So what we're going to do now is we are going to evaluate, or remember, plug in the simplified, not the whole entire thing, just the simplified r of x when x is equal to 2, or our whole, to find the y value of the whole. I ran out of space, whoops. So that'll be our last step. So I'm going to come off here to the side, and we're going to say, okay, r of 2, if I plug 2 into my new equation, I get 3 over 2 plus 3, giving me 3/5. So when I ask you, hey, is there a hole in this equation? You can say yes. At the point, whoops, I don't know what just happened. Are we still recording? Yep. At the point 2, 3/5. So your hole is an actual point. I need you to find the y value and write that as a point. I just threw so much information at you. Feel free to rewatch this again at double speed. Take a look at your notes. Let me know if you have any questions. I look forward to seeing you on Monday.